Hello, everybody,
MoNaCo here.
and Milks.
We're in our sixth video of the
Something
unit.
like that. Yeah.
Yeah. Page 25. I mean, you're almost into this packet. We're going quick. It's second semester. You should know the routine by now. So this is responsibilities on you. If you're not watching your homeworks ahead of time,
Learn it, practice it.
enjoy
Here we
playing
go.
catching up and not getting the grades you
Ooh,
deserve.
sounds like a brain cramp to me.
Bummer.
Anyways, let's get into the heat of reaction now.
Right.
Now, heat involved in chemical reactions.
Right. We want to know how much.
How much heat?
This is actually really a reference table lesson.
Yeah, it's really just how do I use table I.
Yeah, because we were doing physical changes, heat going in and out of those. Let's just spend a minute and talk about some chemical changes and how you might see those and how heat is involved in them.
Yeah. So heat flow in a chemical reaction. Endothermic, of course, is heat entering the system,
Right,
and that is going to give me a positive delta H.
right. And delta H means change in heat.
Correct.
Enthalpy technically is
Yeah,
the
we'll
term
learn that term in a few units.
in kinetics. And also know that in a endothermic reaction, if heat is included in the chemical reaction, it'll
Ooh.
show up on the left-hand side
Right,
of
because
the
it'll be
arrow.
added like a reactant,
Right.
just like a
In
an
order for
ingredient.
these 2 or 3 things to react, you got to add some heat, so it's included as a reactant.
Yeah, there you go.
Good, good. So exothermic is the opposite, heat exiting the reaction or the system, and we're going to have to show that as a negative delta H, and a negative heat of reaction, which might be counterintuitive because of the negative sign, but the negative just means it had lost it.
Yeah, so it's leaving, and we would find that on the product side of the reaction in an equation.
Right, so this would be listed as plus energy on the right-hand side of the arrow in the reaction.
Good. Okay. All right. We need to show real quick what we're talking about, a little drawing.
Right, and we're going to see these potential energy diagrams more. Mr. Milks will narrate while I
Okay.
Right.
All right. So we're just going to kind of talk about the potential energy of the product and the potential energy of the reactant real quick. Okay. And the reactants are always going to be on the left. The products are going to be on the right. And let's see which kind he draws, and I'll tell you if it's exo or endo. So he draws it, and then boom. And now look, the reactants had more energy than the products, so that heat was leaving the system. Potential energy of the products is less than the reactants. That middle piece is the delta H. So we'll get into how we calculate that, but we're not actually going to calculate that.
No, we're not calculating that. And just notice how the products are lower level, so we lost some energy.
Right.
If we lost the energy, it's got to leave the system.
Exo.
Exit the system.
Exothermic.
And I did this in red because exothermic would feel hot to you and I.
Ooh, here we go.
Okay? So we would feel that heat energy coming out of the reaction as, wow, this got hot, mister.
Right.
And so let's check out the other.
Okay.
Oh, forgot to label it.
Yeah, exo. I love how he writes it all out. It's so nice. All right, cool.
Got to do it right. Moving along. Sorry, stop rushing.
No, move. All right, so now we're going to have another curve, and you can guess that if it's going to be endothermic, it's going to be opposite. The heat of the products is going to be higher than the heat of the reactants, okay, or the potential energy of the two. Okay. We will get into these in much more detail in a later unit, but a little foreshadowing never hurts, and it really kind of shows what we're talking about in a reaction anyways. I will have a positive delta H. Notice the product side is higher than the reactant side as far as energy.
So you had to gain energy to get up to the new stuff. And this would feel cold because it's going to suck energy out of the environment around it. So you put your hand around this test tube, it would take the energy from you, and it would feel cold because your heat is leaving you.
Correct. Okay. Some calculations now, and here's the reference table. So reference table I is going to list a whole bunch of reactions for us.
With all the nomenclature, solids, liquids, gases, pluses, and all the good stuff.
We're going to have to pay very, very careful attention. Okay, and basically to calculate delta H, it's the products minus the reactants always.
Right. So like after the reaction, whatever energy they had, minus whatever energy they had in the first place.
True, and we do it in that order so we get the correct sign on our delta H.
For Exothermic, we want it to be negative. Endothermic, we want it to be positive.
And then this is kind of what we were talking about up there. But in table I, what we're going to do is you'll see there'll be values for these particular reactions.
Right.
And if we happen to play games and double the amount of reaction,
right,
we will have to double the heat.
Mm-hmm.
If we half the reaction, we will
half the heat.
There you go.
Mm-hmm.
And the other game we can play is I reverse it.
Right. If I flip the reaction, so if I take the reactants and make them the products, literally flip the reaction around 180 degrees, I got to do the same to the sign.
Yeah, we got to flip it because now it's going to be endo if it was exo and vice versa.
Because one thing we haven't talked about yet is that you can run reactions in reverse. You can force them to go backwards. There's a whole unit on that later.
Some of them, yeah.
Most reactions can be run backwards and forwards.
Yeah.
If you do some fancy chemistry. So moving on, let's look at table I.
Table I. So some quick examples. Now these are, of course, right in the reference tables. Here's a common one. Mr. MoNaCo's, it's not a combustionist though.
No, this is the formation
Synthesis.
of carbon dioxide
Yep,
with carbon
synthesis.
monoxide. Synthesis
Correct.
reaction.
We
Sure.
could look, if this was a problem, you could look it right up in table I and you'd scroll over and you would see it has a delta H of
negative 566.0 kilojoules per mole. And remember, joules are units of heat, and kilo means 1,000. So 566,000 joules for every mole of reaction that happens.
Right.
There's that good old mole.
There you go. And it's because it's negative, we got an exo.
Good. And so here's a sketch of the potential energy diagram.
If it's exothermic, heat is given off. So my reactants have to have a lower energy than the products have to have a lower energy than the reactants.
I did make a mistake on that.
Yeah, I see the
I always
P.
get it backwards.
Yeah.
The P and the R belong in different spots.
Right.
So let me try that again, and I'll get it right this time. So the reactants are on the left, products are on the right, up over the hill, and then down lower than when you started.
There you go. Good.
Good.
Okay. And we can see from the diagram there that heat is exiting the system.
Right.
I'm at a lower heat to finish.
Carry on with the next one. I'll finish up my labels here.
Sweet. All right, another one. Nitrogen combined with oxygen to make NO2 gas. Pay special attention to the gas. These are the phases here.
Yep.
Sometimes that'll trip us up. I see that that's a positive 66.4 kilojoules
So
per
I
mole.
know right away that's endothermic reaction.
There you go.
Cool. And a sketch, always going to have the reactants on the left, products on the right, PE on the y-axis, and time on the x. This one means that it absorbed heat, though. So I got to start low, go up over the hill, and end high.
Because it ends in a higher heat.
The reason why there's a hump in the middle is something we'll talk about later on in the year, but it's very important. We'll get there some point later.
Yeah,
when it matters.
Yes. All right, here's another one. Formation of water vapor.
So all of them are in the gas phase. Yeah, this is funny too because you'll also see this formation of the liquid H2O in the chart. If you're checking out table I, you'll see something very similar to this, except you'll see H2OL as a product.
And notice
actually
it's right below it.
makes it does make a difference in terms of the amount of energy. So
We will see because it's actually we're going to do both as examples. So
negative delta H, that must mean it releases heat. So it has to be exothermic.
that's right. We release the students from class, they exit.
Yep.
So it's exo.
Just do here PE time. Hopefully you'll see that the reactants are there, products are there, and so this one releases heat. So we start with a lot more energy than when we ended.
There you go. Heat is exiting. Okay, now here is the same equation right below the one we were just doing.
But what'd you do?
Well, first of all, we're making water liquid instead of water vapor, and I
flipped it.
flipped it.
So yeah, there is a different amount of energy involved here.
Correct. So instead of negative 571.6,
It's positive.
it's positive.
Cool.
So because
So
I
it's
flipped it, I
positive,
flipped the sign.
That means it absorbed heat. It has more heat after it's done than when it started, which means it was endothermic. And so when I sketch my PE diagram, we got a PE over here, time down there. And so we got a reactants and products. And so I started out with less energy than when I ended. There it is.
Good. So we're going to see that the bulk of our practice after we do this is basically using table I
Yeah.
Can I find the reactions? Can I figure out what to do with that number?
Yeah.
Do I double it? Do
As
I
a matter of
half
fact,
it?
all the practice is kind of you self-derived. You're going to pick a reaction off that chart and describe all of it, following the examples that we just did in this video.
Sure. It almost should be. I want to see if somebody actually flips one themselves or halves their double. Halves their doubles ones themselves.
Love it. That means they're really paying attention. Woo-hoo! So you got to know where to find the heats of reaction. That's reference table I.
Yep.
It comes after H and before J.
Hey, all right.
And if a reaction is exothermic or endothermic, based upon the delta H value. Okay, so thanks for watching. See you later.